we should start. As a comment to previous lecture by John Chalker, I think there is a clear Z2 pattern in how sunny days follow rainy days, vice versa. And I've been testing this for 2 weeks and it never failed. We'll see how it goes. The QED and graphene, that's where we left it yesterday. You start with microscopic picture describing interactions for species of Dirac systems, and find that on the perturbation level there are log divergences, and then you try to analyze these log divergences and find RG flow for various quantities, velocity renormalization that we discussed yesterday, and also mass renormalization. And so mass renormalization, we said everything, but very briefly. So let me take maybe 5 minutes out of today's material and repeat that. Mass renormalization is a more conventional topic for QED. Velocity renormalization does not occur in real QED because it's Lorentz invariant. Mass renormalization does occur, and the story in graphene is really very, very similar. If you introduce a perturbation that creates mass, let's say by putting on a substrate that breaks a B sublattice symmetry, you get gap opening in the Dirac spectrum, and you can describe it by mass term. And then if you look at interaction corrections to that, there are log diverging corrections that arise from vertex corrections of this type, and you can ask how bare mass that you have on the lattice scale, how it flows under RG, and what it becomes with it at larger length scales, and can treat this log together with various other logs that we found, and show that the RG equation for mass generates this exponent, which is related to the velocity exponent that we derived yesterday, and it's similar to how radiative corrections in real QED have been treated by Weisskopf, and also how spin-hole gap enhancement has been discussed in Kane and Milley paper. Right now, if I'm interested in a real system, graphene and boron nitrate, then I have to take into account the period mismatch that leads to superlattice structure, and that means that if I try to introduce a mass term in my Hamiltonian, then it won't be spatially uniform. It will be spatially modulated with that period, and so I have to extend RG to treat that. Also, so this is a quick review of what we said about experiments. When you place graphene boron nitrate at crystal axis nearly aligned, you find that there is a gap that you see from transfer measurements activation behavior that depends on the angle between crystal axis, and you would like to understand this dependence. Dependence is such that increasing the angle suppresses the mass. Twist angle going down means gap going up, right? And so you would like to understand the scale, also this dependence, and you can do that by adding a spatially modulated mass term to the Dirac equation, and then if you before you turn on interactions, you can ask what this term does on a single particle level, and it will open a gap at the Dirac point, but only at third order perturbation theory, because you need to get a contribution in which the modulation vectors add up so that you get a zero net vector. Each of these produces Bragg scattering with the superlattice vector B, and you need scatter 3 times in 3 different directions to get back to where you started. And so you need to go to third order in this M3 parameter to get a gap, and because of that you get third order, you get suppression compared to first order value, and so the gap, even if you take the M3 value for of order a few hundred Kelvin from Ab initio, which is predicted by Ab initio, for example, in this paper and other papers, then at third order you get a gap which is about 10 times smaller than the experimentally observed values. So to explain this enhancement, interactions might be to explain this discrepancy. The interactions might be something useful to consider, and so the way renormalization proceeds is that you consider vortex corrections to each vortex of this third order diagram that opens a gap. It's a self-energy insertion and the Green's function, single particle self-energy insertion and Green's function for non-interacting electrons, Bragg scattering on the spatially dependent mass term, and then that we have to renormalize by adding interactions, and so these vortex corrections will generate log diverging contributions that will renormalize vortices, as we discussed before in QED spirit, also the Green's functions, and we have to put all of that together, and the resulting RG flow equations for mass and for velocity should be combined and studied together, and so the gap flows basically with the exponent, which is 3 times the single vortex exponent for the mass, minus 2 times single velocity exponent and that arises simply from 3 vortices here and 2 Green's functions here. And then because there is this factor of 2 difference between beta mass and beta velocity, there is some combinatorial factor that produces a fairly sizable exponent and a rapid enhancement. And then, if you want to make a complete story out of it, you have to think about what happens at different length scales. For example, what we said in the previous slide was good at length scales from lattice scale up to the more rare superlattice scale, and then if you go beyond that, then your particles your particle energy becomes smaller than your particle momentum becomes smaller than the Bragg scattering momentum, and so you have to treat this perturbation as a zero Bragg scattering perturbation. As the spatial uniform mass term. And so then renormalization proceeds in a slightly different way, in this more conventional way that we mentioned, and then you have to, so there are 2 stages of RG. It first grows rapidly, then grows less rapidly, and then it terminates when you reach the length scale at which the gap growing as a function of length scale reaches the particle kinetic energy that you computed without accounting for the gap. So there is a self-consistent condition for where you terminate the renormalization group, And that determines the length scale and therefore the gap size that you predict from this analysis. And so that's where these numbers come from. Okay, so I think that's the end of what we discussed yesterday. So conclusion is that interactions are probably important to understand the observed size of the gaps and also produce the right angle dependence, and can be tested experimentally, but that's probably coming. Okay, any questions on that? Yeah.
Do all the masses allowed in graphene Hamiltonian renormalize the same way? Like if I consider the staggered mass and the Haldane mass, do they renormalize in the same way?
So Haldane mass is what? So I mean the Kane-Milly paper, I think what they discuss is renormalization of Haldane mass, right? So it renormalizes as a mass as a spatially uniform mass. And I think the reason is that even though there are terms involving different values, the interaction effects, because of long-range Coulomb interaction, they don't couple values. So because of that, all renormalization proceeds in the same way. Mass is spatially uniform. If it's not spatially uniform, then you have this more complicated story. And then, so here it's actually interesting because because of perturbation, going to third order perturbation theory, your bare non-interacting gap is smaller, but then renormalization proceeds faster, and somehow these two effects nearly compensate each other, and the resulting gap you predict is comparable to what you would get for spatial uniform modulation. Yeah. Okay. So let's see. Just to clear everything from the last lecture, I got. Someone asked me at the end of the lecture, why are we doing it QED fashion, rather than doing the conventional condensed matter field theory? Is there any reason for that? The answer is no. I chose to do it, first of all, I thought it will be more fun to do it because it will be a way to exhibit analogy with QED, not just verbally, but on a formal level. Well, also, of course, to show off. But there is really no fundamental reason. Also, perhaps there are more people with QED background here than with condensed matter field theory background. So I thought. Right. Then also someone asked about can we understand the sign of velocity in a simple way? William asked, and I thought this question wasn't relevant and rushed to suppress it, and then I thought maybe it's actually was interesting to discuss. And I think so. The question was, can we predict, looking at the interaction, whether the velocity will be renormalized up or down? And I think the general situation is that interactions which are mediated by particles which are slower than fermions, lead to velocity renormalization down. They generate velocity reduction and mass enhancement, whereas interactions mediated by particles which are faster than fermions, such as photons in our case, or instantaneous interactions, they produce velocity renormalization up. At least on perturbation level, this is very clear if you think about this. this diagram, and then there are more complicated cases about what happens in a strongly correlated system, like if you take helium-3, then helium-3 interactions with helium-3 are dominated by contact short-range interactions, so it should be non-retarded and would produce, according to what I said, velocity enhancement. However, people believe that helium-3 is so strongly interacting system that it's actually on the verge of some stoner type instability, and so there are many low energy excitations, spin fluctuations, which are slower than quasi-particles, and so they produce renormalization that brings velocity down and enhances mass. And I think that's kind of general situation. I thought if there are I know any exceptions, and I actually don't. So I hope that clears everything and leaves me with about an hour. Yeah. Any questions? Okay. So I thought what would be a fun topic to something inspiring to talk about at the end, and probably there's nothing more inspiring than superconductivity. So I decided to change the plan a little bit and talk about superconductivity in the remaining time. I will start with general review. I don't know how many people have background in superconductivity. Unfortunately, no one talked about superconductivity before me. So I will spend maybe 15 minutes talking something very general, but perhaps that may be useful. Actually, how many people studied superconductivity, just for my information? Oh, okay. Yeah. And how many people didn't? All right. So I will divide time proportionally. Right. So superconductivity was discovered in 1911 by Cameron Onnes, who observed that when he cooled down by the new technique that he developed, when he cooled down mercury to a few Kelvin temperature, resistivity suddenly dropped, and he thought, dropped by many orders of magnitude, and he thought that there was some circuit breakdown, and spent a long time searching for circuit breakdown, and then of course it turned out that his apparatus was perfect, but it was mercury that did that, and resistivity of mercury vanishes below this temperature, and that temperature is the critical temperature for transition from a normal state where resistivity is finite to a superconducting state where it's zero. And then that started a long investigation of superconductivity, both experimental and theoretical, and experimentally more and more materials have been known with temperatures, superconducting temperatures, critical temperatures being higher and higher, and recently, 100 Kelvin barrier has been reached, and in high TC superconducting materials, we have superconductivity at above nitrogen temperature. And so manifestations of superconductivity is that resistance becomes zero, and by zero I mean really zero. Current flows in a dissipationless fashion and can persist forever. And it has been tested, well, not forever, but for years, that has been tested. And also there are striking effects like Meissner effect, that if superconductor expels magnetic field, and because of that, it can be suspended in magnetic field and levitate above a magnet. And the mechanism for that is that in magnetic field there are supercurrents which are induced in a thin layer near superconductor surface, and these currents produce magnetic field these currents shield magnetic field from the outside, and it becomes zero inside, and so the superconductor becomes a perfect diamagnet, and as a perfect diamagnet expelling magnetic field inside, it will repel from outer magnetic field and levitate. So, if you were living 150 years ago and would like to show levitation to your friends, you would have to play some trick, like this gentleman who attached himself by thin wires to the ceiling and pretended that he levitated. But if you, now you can benefit from having superconductivity at your disposal, and if you board a maglev train that levitates above the rails, then you will be doing the same thing as the gentleman, but together with the train, and no tricks, pure science. And so these trains not only they levitate together with people within them, but also they're very fast, and so that's the number I picked from the web when I was teaching this class a few years ago. Maybe it's higher now, but that's a record speed for rail vehicles a few years ago. Right. So on a microscopic level, superconductivity is an example of a broken symmetry state, and so I don't think anyone talked about phase transitions and broken symmetry in detail before me, and Joel mentioned it, and several other people did. But so let me, for the sake of completeness, say that again. So if you have a Hamiltonian describing your system which is invariant under some symmetry, and then the ground state is not invariant, then you get a ground state in which symmetry is spontaneously broken, and then you get ground states have degeneracy, which is finite if you break discrete symmetry. And the classic example of that is this phi-4 theory with the effective Hamiltonian that has positive curvature at temperature above the transition, negative curvature temperature below the transition at phi equals 0, and then it develops two minima which are equivalent but distinct. And so the system, if it was here at temperature above the transition, will go here or here, temperature below the transition, so it will be two different states. And if you have the same type of situation, but the degeneracy is infinite, then you get the continuous symmetry breaking. And that's the example that we're interested in. If you break continuous symmetry, then you get a continuous family of ground states, each labeled by continuous variable. In this case, it will be a superconducting order parameter phase, and that continuously degenerate manifold of ground states typically has a non-trivial topology, and there will be defects with non-trivial topological quantum numbers, in this case, in the superconducting case, vortices, and then there will be various other manifestations that probably should skip, and so this is how this looks in a superconducting state, and so the effective potential is, for a superconducting state, is described by Ginzburg-Landau theory, which is the same type of potential as for phi-4 theory, but the field is complex, and because of that, when symmetry is broken, you get a continuous degeneracy, which are the states over here, and that's what often called Mexican head potential, and so that the symmetry breaking that we have in this case is continuous symmetry breaking, is described by breaking of global gauge symmetry. If I take the field phi, which will be associated with the superconducting condensate wave function, then giving it different phases, I get different states, and so I can get I can get a continuous manifold of different superconducting states as a result of such symmetry breaking. And the manifestation of non-trivial topology, so non-trivial topology is here. If you take all the states that can be realized as a result of continuous symmetry breaking, see that it's a circle, and the circle has a non-trivial homotopy pi 1, right? So as a result, you can construct defects which will be topologically non-trivial, and as a result, stable, like vortices for each of which the phase winds by 2 pi going around the vortex, and then you can do it both on a superfluid and a superconductor, and then Bose-Einstein condensate. So it's symmetry governed and therefore very general, and it's a clear manifestation of topologically non-trivial character of the state enforced by continuous symmetry breaking. Right. And so this was an artist image, but this is actually data from that same paper, where they take a bucket of superfluid helium and then spin it faster and faster, and then image vortices that appear in the bucket as they increase the revolution speed. And these are pictures from experiments on cold atom BEC, where people have flight time techniques for imaging vortices, but from symmetry point of view, it's the same story. Okay, so that's symmetry. Any questions? Yeah.
So the gauge symmetry is special because it's like a redundancy in the description, in the way you write the Hamiltonian or something. So why is breaking gauge symmetry? How is that different from breaking like parity symmetry?
Well, from symmetry point of view, there's nothing special except that gauge symmetry is continuous and is relevant for superconductivity. There are magnetic systems where broken symmetry would be a rotational symmetry, continuous rotational symmetry in spin space, or there are liquid crystals where broken symmetry will be continuous rotational symmetry in the water parameter space, which is described by space rotations. There are similarities and differences between all of these, but we maybe postpone. Yeah.
Strictly speaking, isn't you right in the sense that it's not a symmetry, it's just a redundant way of writing photon dynamics? You can't really break it, strictly speaking, but it's only redundancy.
No, gauge symmetry is spontaneously broken.
But what does it mean? You said the system prefers a specific gauge?
Yeah. Yeah. Yeah, like in a magnet. It decided to be magnetized this way and not that way. So that's it.
Yeah, but I thought we said things shouldn't depend on the gauge that we choose.
No? No? So no? I can measure. So this phase is
you don't have a fluctuating gauge.
the phase is, as soon as it appears as a result of symmetry breaking, it becomes observable, open for experimentation using in the devices, etc. So it's not, it's not some mathematical transformation that relates different phases.
But that's how it starts, right? It starts as a mathematical transformation, right? So
I'm not sure. Sorry.
Yeah, it seems like it should be different. Yeah, I don't know. It seems like it should be a little bit different from other symmetries.
So, you can make a contact between two superconductors and by doing transport measurement, measure phase difference. So it's not, it's not anything arbitrary. You can enforce phase difference by applying magnetic field and current, etc. So phase become an observable which is as good as, mass, charge, etc. Yeah.
I think the picture is quite different because you had a fluctuating gauge that comes to the pattern for CO.
Yeah, phase can.
The unitary gauge at least you can acoustically absorb.
Yeah, but phase can fluctuate, but in the same way as my weight fluctuates because molecules of air come and go. But there's nothing.
Absorbed into the gauge, the unitary gauge at least.
Yeah, but so fluctuations are part of everything. Thermal, 0 point, and phase exhibits both of them. Thermal and 0 point fluctuations are part of that. Let's not.
I'm just saying that the complex particle force theory is somewhat different physics once you add a fluctuating engagement to it. So if you add, d mu plus
Yeah.
I
So on top of the spontaneously broken state with a phase, there will be some fluctuations. But so what?
No, but, okay.
Excuse me?
Yeah.
As we all know, infinitely large, flat, 2D system, we don't have VC. So what kind of superconductor in 2D system you are talking about? It's about a
Yeah, so fluctuations, okay, so one can take this question further and say that if fluctuations are strong enough, then they can suppress the superconductivity entirely. So if you go back to that picture, if you found a way to enhance fluctuations so that the system will become totally messed up in that Mexican head, then it will not know what its phase is anymore, and you can do it a variety of ways, either by irradiating superconductor by some external radiation, or by putting it in a low, making it low dimensional, or perhaps other ways. So one can mess up it in different ways. But if you don't have strong phase fluctuations, then we are safe. So let's maybe postpone that a little bit. So the origin of superconductivity. Let me. This is probably last generic slide. The origin of superconductivity was understood by Barden, Cooper, and Schrieffer almost 50 years after superconductivity was discovered. And the picture that I've been talking about is part of that general understanding, but they also developed, and actually that picture came before their work, but due to London and Landau and Ginzburg, etc. But what Barden, Cooper, and Schrieffer provided is a microscopic picture that explains microscopically what happens when a system goes in a superconducting state, and how the macroscopic coherent state with global phase arises, and the state is characterized by a coherent macroscopic wave function similar to Bose-Einstein condensate that perhaps is more familiar to some people. Has applications. Superconductivity has various applications in nano devices, which behave as, on one hand, macroscopic, but on the other hand, fully quantum mechanical systems, and have new properties that can be used, like this superconducting teapot can be, because it's superconducting, it can be shuffled back and forth above the magnetic rail, and then there are many other, perhaps even more useful applications like Josephson junctions and qubits that rely on this macroscopic character of quantum mechanics that becomes available in superconducting systems. So the essence of BCS theory is formation of Cooper pairs. So Cooper pairs are, often people say that Cooper pair is a bound state of two particles, which is a composite object, a boson, and then we should think about superconductivity as a Bose-Einstein condensation of these compound objects. And so this is, okay on the verbal level, but is not correct microscopically. In fact, in a metal where superconductivity arises, at short distances, the interactions dominated by Coulomb repulsion. So electrons never bind in a compact two-particle objects. Instead, they move sort of freely, but become coupled due to phonon-mediated attraction. So it happens that the electron goes through a metal, and then it couples to atoms in the crystal lattice, and they move in response to electron passing by. But because they're heavy and move slowly, the trace of the electron that changed the atom positions is left for a much longer time than electron stays there. So electron moves far away, and atoms still remember that electron been here, and then the next electron comes and feels that distortion and is being attracted to that distortion. You can say that electron is negatively charged and ions are positively charged, so it pulls ions a bit in, and then when it moves out, the ions stay a little bit at a little bit higher density, and then the next electron comes in and is attracted to that excess density. And so that's the electron phonon interaction that mediates attraction. And two things which are important. First of all, the resulting correlations are very large length scale compared to crystal lattice. The correlations between pairs which attract, the correlation length scale can be 100, 1,000 times crystal lattice spacing. Yeah.
On this picture of one electron pass creates a higher density of ion, then another electron pass just after it. Why isn't there lots of electrons that are just passing through? Because if you have your first electron, your density is higher, then you have another electron that will come by in the same path. So the density will still be a bit higher. So why isn't there more and more electrons passing by the same?
So we are not okay. So I'm trying to make it too simple. So I'm not saying that all electrons will be channeled in some way in a particular direction. They're moving sort of randomly, freely in all different directions. However, the electrons which are counter-propagating, they are most strongly coupled by this effect that I am describing. Because if you have an electron that moved this way and it leaves some trace, some atom distortion behind, then electron that will go in any other way will be able to couple to it. But most strongly coupled will be the electron that is counter-propagating and goes the same way, because it will sniff the trace left by the first electron for the longest time. And so this electron should be, the pairing occurs for electrons which are counter-propagating, but they don't have to be at the same location. They just counter-propagate, and it creates some correlation between electron states on opposite points of the Fermi surface, because those are counter-propagating electrons. That leads to superconductivity. And so the pairs, yeah.
How does spin come into this?
So spin comes in this way. I mean, you can have pairing due to you can have pairing between particles with different spins. This mechanism is not particularly spin sensitive. But then once you have pairing interaction, you have to decide what spin configuration, what spin correlation of pairs it favors, and it's a long story that I don't want to get into. So today we'll be always talking about singlet pairing, nothing else. Yeah.
It seems that if you have attraction, it's kind of natural that electrons want to stay nearby, and somehow it seems to favor.
Yeah, so
S-wave symmetry.
yeah, so you might say that the same attraction might work for electrons which are co-propagating, because they would, each of them would perturb a lattice, and electron would, the other electron would feel it. However, for these electrons, Coulomb interaction will make pairing unfavorable, because they stay together at the same point for all the time, and therefore Coulomb interaction wins. I mean, typically in metals, Coulomb interaction is stronger than this phonon interaction. So it's kind of a miracle, and was a puzzle for a long time why Coulomb interactions don't suppress this superconducting attraction. More on that later. Right. So the first point. Sorry. So there are two main points. Is that one is that it's co-propagating and on opposite side of the Fermi surface, and then the other, as a result, the correlations are pretty long range, and so these Cooper pairs are pretty fluffy, and so they almost never come in close proximity to each other, meaning that the distance between them is typically larger than the screening length for Coulomb interactions in the material. As a result, the effect of Coulomb interactions is smaller than one might expect, but there's more coming. So if one takes this as a starting point and then puts it through math and does many-body analysis, one arrives at the formula for the energy scale that describes the gap that opens up at the Fermi level when electrons pair up. And this energy scale, the BCS formula for the superconducting gap, is exponential is in the attraction strength. And the prefactor is of order of Debye's frequency, because it's because it's phonons that produce attraction in the first place. And so that's the result for the energy gap. The result for critical temperature is that there is a universal relation between the energy gap, zero temperature, and critical temperature at which the superconductivity disappears. And so this exponential dependence explains a lot about superconductivity, in particular why superconductivity occurs at such low temperatures. If you take most materials, superconductivity is few Kelvin temperature, sometimes 10 Kelvin, in very rare cases 100, maybe two cases known as 100 Kelvin or so. So it's fairly low temperature, whereas in solids everything is of the scale of EV. Right, the characteristic scale for Bloch bands in a metal is Fermi energies, or the EV, etc. Right, and superconductivity is typically much smaller scale, so that kind of follows from this exponential dependence, because if you exponentiate any number, any negative number, you will typically get a very small number, right? So that's the essence of BCS theory. Now, question to you: are you comfortable with this, or do you want me to spend some time deriving it? We got some time that we can maybe. So if you want to see this derived, I can do it maybe in 4 or 5 slides. Huh? I didn't hear that. Well, you said yes? Yes. Okay. So, but I will be quick for the sake of other people. All right. So you start with a Hamiltonian, which is two particle interaction, and so this is somehow a model Hamiltonian in which phonons don't appear explicitly. This interaction represents an effective interaction due to this phonon-mediated effective interaction, which is attraction. And we'll make approximation 1 replace it just by a negative constant, forget about spatial dependence, spatial dispersion, etc. And then the approximation 2 that one can make is that one should focus on the terms. So this is basically two particle scattering, where you have particle 1, particle 2 coming together and then interacting via this potential. And so all quantum numbers in principle are allowed, which not forbidden for spin conservation, momentum conservation, etc. But because of that intuition that we have that the particles which are pairing are counter-propagating, it's useful to suppress part of this Hamiltonian and focus on the terms that corresponds to incoming particles having opposite momenta, and also, if we're talking about pairing in a singlet channel, opposite spins. One can relax it later. But that's the starting point of the BCS Hamiltonian. So if you do this, then you get a Hamiltonian that looks almost the same, except that I did what I said. I replaced arbitrary incoming momenta by counter-propagating momenta, and arbitrary outgoing momenta also by counter-propagating momenta. So these two particles will have counter-propagating momenta and will be somewhere here on the Fermi surface. And then this process will describe scattering to a state near the Fermi surface with some other counter-propagating momenta, and they can be in arbitrary configuration relative to each other, right? So if you start with that, then you can derive a simple mean field for this Hamiltonian. You can take that operator that we introduced for pair creation and try to, given that we have many particles, you expect that this operator will acquire a non-zero average. You can define a C number, which will be an expectation value of that operator. And don't ask me how an operator which is not particle number conserving can have a non-zero expectation value. That would take us a bit further than I want to go. So if you just postulate this, and then we can justify it later, that you can introduce a C number as an expectation value like that, then it's also useful to define a quantity which is expectation values of these pair creation operators times the pairing interaction. And then the mean field approximation is constructed as follows. You expect that each of these things will be sort of close to its expectation value, and so you, as you always do in the mean field case, you take the Hamiltonian and then add and subtract the mean field value that you expect to represent microscopic quantity well in the mean field approximation, and then you do the expansion and extract terms which are the quantum variables minus their expectation values, and then declare that their product is that this difference is small, and simply suppress that part. So I'm not doing anything different from what you do usually when you derive mean field approximation for Heisenberg ferromagnet or any other fluctuating system when you go from fluctuating variables to mean field variables. And I'm doing exactly the same thing here. And after this is done, you end up with a Hamiltonian which is quadratic. And there've been so the single particle, the free particle part, I don't write, it remains unchanged, but also that part turns into this quadratic Hamiltonian. There is a C number here which I'm going to suppress, but then there is a non-trivial part that will be useful. And so this quadratic Hamiltonian is what people call Bogolyubov Hamiltonian for a superconductor, and now we can take this quadratic Hamiltonian and diagonalize, and it can be diagonalized because it's quadratic, it's trivial to diagonalize it. We can just do canonical transformation on particle creation and annihilation operators. Just be sure that we preserve canonical commutation relations, and so that's a quick reminder what canonical transformations are. We can do canonical transformation on any set of Bose operators or Fermi operators using a unitary transformation. Also, we can make more complicated canonical transformations that mix creation and annihilation operator. And this is a simple example. If you take creation and annihilation operator for fermions, you can interchange them, and that amounts to replacing particle state by whole state and vice versa. And that's a canonical transformation. So these canonical transformations are kind of a mixture of both of these. We're doing this and that at the same time, and using this canonical transformation, you can check it's canonical, preserves commutation relations. You can diagonalize the missing slide. You can diagonalize the Hamiltonian and obtain quasi-particle spectrum. All right, so one slide missing. Sorry, I was careless deleting slides. Right, so what happens is that you get the Hamiltonian in terms of these A operators, which will be which will look like this, and E will be a square root of single particle energy plus delta, the order parameter. Right. So here in a stealth way, I already introduced the superconducting order parameter, which turns out to be defined through pair creation operator expectation values in this way, by multiplying them on pairing interaction. And so what can be shown by doing this calculation is that it is this value that will correspond to the gap that opens up in particle spectrum on the Fermi level. Sorry for missing slide. So then the last thing we want to do is to write down self-consistency equation for the superconducting gap. And if you take the formula by which it was defined and then take expectation value of all operators and then express them through coefficients of this canonical transformation that we introduced, then you get this, and that gives you a self-consistency equation that determines the order parameter, and depending on your interactions and also on temperature, which you can put in these equations, can be zero or non-zero. And so this equation plays the same role as the self-consistency equation by which you predict whether your ferromagnet is in a paramagnetic state or in a ferromagnetic state. And so once we obtained it, too quickly, I admit, but we can analyze it and ask what's the solution for this equation. And one simple thing we can do looking at this is just think about how we evaluate the sum. So one realization is that because of what we said before, that the superconducting gap is going to be much smaller than Fermi energy and all other characteristic scales for particles, only states near the Fermi level are going to play a role, and states far away from Fermi level don't contribute too much. So even though there is an integral over all all states, one can show that only vicinity of Fermi surface matters, and because of that, it's convenient to simplify the integration and go to the vicinity of the Fermi level by replacing integral over three-dimensional K-space by integral over one-dimensional energy and multiplied by density of states. And if you do that, you get a contribution of states near the Fermi level in this form. And then I also account for the fact which we didn't, we knew and talked about, but didn't introduce it explicitly in the formalism, that only energies which are of order Debye's energy near the Fermi level contribute, and so then your self-consistent equation simply gives you an equation like that, where this is a simple integral that you can evaluate, and as you can see, this is basically d epsilon divided by epsilon. Forget about delta for the moment. So that's a log. And this log would be divergent log in the absence of delta, but delta will cut the divergence at zero energy, zero epsilon, and so it will take a form of log of delta appearing as a infrared cutoff, and that will lead, solving this for delta will lead to this exponential dependence. So that's all. And then if you want to obtain critical temperature, you can, if you don't worry about coefficients, you can just say that by order of magnitude, critical temperature should be of order of that energy gap within some factor of order 1, and then it turns out that this factor of order 1 can be calculated from the same type of approach, and it turns out to be approximately 3.5. So that's where all this comes from. And so this relation between energy gap and critical temperature is testable, and was one of the first experiments that confirmed BCS theory predictions, and it works surprisingly well even in the materials where people expect strong deviations from BCS pairing mechanism. But by order of magnitude, it should be true, and it does. Right? So that's the end of generic part. Yeah.
Well, where does particle hole symmetry come from in this mean field approximation?
So particle hole symmetry is not a genuine symmetry in this case. It arises approximately because the characteristic energy scale is much smaller than the Fermi energy. So in a sense, it's the same as in graphene band structure. Graphene band structure, if you look at all 20 bands that you get from carbon, they're not particle hole symmetric. It's only because near the zero energy you have approximate particle hole symmetry. Becomes more better and better when your linearization works best, then the particle hole symmetry is approximate but good. So there is a parameter that controls it, which is delta over Fermi energy.
Interesting. It's only due to the fact that it's very close to the Fermi level, any band structure is a line.
Yeah, so you linearize. So the same way as by linearizing block bands, we obtain Dirac fermions with particle hole symmetry. If you don't linearize, then you don't have. There are corrections to that break particle hole symmetry. I'm not sure if I'm answering it right.
No, that's
yeah, I can go a bit further, but I think that's about right. Okay, so can I move on? Right. So now let me talk about two-dimensional crystals. Maybe start a bit before that. So in metals, as we mentioned before, Coulomb repulsion by numbers is stronger than phonon attraction. And if you write a Hamiltonian in which both interactions are present, phonon and Coulomb, Coulomb repulsion is positive, phonon attraction is negative, and one can ask which of them dominates. And if you would have to decide just by numbers, then you would say that Coulomb interaction always wins because it's always stronger. But it turns out that this effect of phonons being retarded and producing some attraction even when particle moved away compensates for their relative weakness and makes phonon attraction win in the majority of cases. And in fact, I think out of all metals known, conductors known, there are about 60% which are superconducting at some temperature, and others aren't. However, so the way you see it in the formalism is that if you put both Coulomb interaction and phonon interaction in that approach I discussed, and you have to do it a bit more carefully than what we did, you find that both coupling strengths appear in this BCS formula, and the phonon coupling appears the way we discussed, but then the Coulomb interaction gives a negative contribution to this coupling, so it suppresses lambda. However, the suppression is not too big because of this retardation effect diminishing the effect of Coulomb repulsion, because particles which attract to each other are typically far apart. You get a reduction in this Coulomb part by this log factor, and so this is mathematical expression for how Coulomb repulsion, even though it's nominally stronger, cannot win over phonon attraction. However, I mean, from this picture you see that there is always a delicate balance of forces, and it's only because of that retardation effect phonons can win. Now, because of that, very soon after all that has been understood, people, yes.
So I remember someone told me, maybe jokingly somewhat, that the only way someone would accept a theory of high TC was if it could predict high TC superconductors. But for BCS, at least, it seems that what we have is...
I'm not working on high TC, so I'm not...
Okay, so, but just for the BCS, it seemed like we have this relation between the size of the pairing gap and the critical temperature, and...
Yeah. So let's
predict BCS.
Yeah. So let's maybe in 2 slides. Let's come back to that, because so as soon as this delicate balance was understood, people conjectured that it's not accidental that all these critical temperatures that we see are so small, and there must be a fundamental reason why temperature cannot go higher than 10 or 20 Kelvin. And actually a lot of effort has been invested into proving this theorem, and the greatest minds of the time, who I will not name, worked on it. But you can see all of it in the literature. Well, at the same time, people started thinking about, are there any other mechanisms which are different from what we discussed? And there is a long path that eventually led to very, very unconventional mechanisms, including the one that produces high temperature superconductivity. But fortunately for me, I won't get into that today. But it starts perhaps with this paper that proposed an apparently innocent, but nevertheless an interesting modification of the BCS mechanism. So let's suppose that the main interaction is repulsion, however, and it's Coulomb repulsion. However, a permittivity, that dielectric constant that enters this repulsion, has a strong frequency dependence, and this is always the case in materials. And this dependence can be particularly strong in polar dielectrics, where you have different ion species in the crystal lattice, and then they can vibrate relative to in antiphase relative to each other, and this polarization will produce electric fields and will screen Coulomb interaction and will contribute to permittivity. So if you have that, if you have a metal which has a polar structure, then you have a repulsion, but this repulsion will have this very dispersive character. And then you can show, as was done in this paper, that if you split this interaction into non-dispersive part, determined by the value of epsilon above these vibrational resonances, and dispersive part, then the non-dispersive part, which is repulsion, will play together with the dispersive part in the same way as Coulomb interactions play with phonon, electron-phonon attraction. You'll get superconductivity without explicitly introducing phonons into the picture, just via dispersive character of permittivity.
What is gamma?
Gamma. So I wrote some single particle oscillator model for this permittivity that we'll learn when we study E&M, and there is some damping constant, but it will never appear, will not be important anyway. But if you yeah. We'll come to that. So then soon after, so this was 1962, more than 50 years ago. Then soon after, people proposed an idea that we can perhaps, so this is exactly 50 years ago now, we can combine different materials, some of them being good conductors and other materials having very strong polarization modes, to produce composite materials that in which we have benefits both from having a good conductor and having good vibrational modes if they are not available in one material. And in particular, in this paper, Little proposed using organic polymers with organic molecules attached on the side, and said that because of this attraction that you just mentioned, we'll get a pairing interaction, and because in organic molecules the main constituent is carbon, and carbon is very light, and the phonon frequencies can be very high, you can get a very sizable attraction. And similar ideas were proposed by Ginzburg, who was thinking about layered structures of having a superconducting film, and then some dielectric with polar phonons on top, and then that started an avenue of research that continued for some time. Like I said, using complementary materials is very attractive from theoretical point of view, because you can have material with high density of states, but perhaps not very strong intrinsic electron-phonon interaction. And then if you combine it with polar dielectric placed around it, then you might have a very strong dispersive part of Coulomb interaction. And indeed, you can have attraction. So, for example, if you take a very polar, one of very polar dielectrics, strontium titanium dioxide, which, and this is the permittivity frequency dependence, optically measured. Then this is absorption. So these resonances correspond to this single. Each of them can be modeled as a single resonance by this formula that was in the previous view graph, and the width is due to damping. But then if you look at the real part, of epsilon, then you see that at near each resonance it changes sign, and there is a range of frequencies where it's negative, and that means that your interaction, where range of frequencies is attraction, like here, right? And so that that research continued for a long time, and there have been various mechanisms invented along these lines. Experimentally didn't go anywhere because at the time all superconducting films that people could create, even if they thought about them as being quasi-two-dimensional, they were actually too thick for this effect to play a role, because even if you think about niobium film, niobium intrinsically has TC of order 12 Kelvin, which is respectable, and it's very easy to grow a niobium film which is very, very thin, but very, very thin means something like 2 nanometers, and 2 nanometers is still larger than screening length in niobium. So the electrons in niobium, even if you surround it with the best polar substrate available, they won't see much, they won't couple much to that substrate. So it's really the case when I think the idea is good, but it was too early for its time, because at the time, really two-dimensional materials with electronic states that would be fully exposed to couple to the environment were not available, and of course they're available now, which is why I'm talking about it. So what we want is a two-dimensional conductor with fully exposed states, and we are not looking for the one with strong electron-phonon interaction intrinsically, because we are going to put a dielectric substrate with strong polar phonons, and so graphene is obviously one candidate, but perhaps not the only one. More on that shortly. So graphene is good. Graphene is good because Coulomb interactions are three-dimensional, as we discussed, and they are strong. And also one might argue that in graphene, if you are near Dirac point, even if you dope it slightly away from Dirac point, you have density of states which is small because it's proportional to your gate voltage somehow. And the density of states appeared in the exponent, in the BCS exponent. So you would say because of density of states being small, it will be exponentially suppressed. However, the Coulomb interaction, interestingly, the Coulomb interaction varies proportionally. So the Coulomb interaction strength, which is reduced by screening, becomes unscreened as you approach Dirac point, and it becomes unscreened in such a way that the product of interaction and density of states basically doesn't depend on doping. Doesn't depend on carrier density unless you go really, really close to the Dirac point at the scale below KT. So the two factors in the BCS density of states, if we go back to that formula that we wrote here, the density of states and the interaction strength, each of them depends on doping. This decreases with carrier density, but this one increases, and their product is roughly constant. Right? So let's see, what time is it? Okay, right. So, yeah.
So usually we want screening to reduce the Coulomb interaction. I think that here we don't want a strong screening.
That's right. That's right. That's right. That's right. So here, right. So like in all high TC scenarios, Coulomb interaction is your friend, not your enemy, and this is the simplest case of that type. Right. So we have so for graphene there are good news also, but if you start calculating, you find that it's not entirely sunny. You have 4 flavors, and you can only have pairing because you have this K minus K constraint. You can only have pairing between states with time reversal symmetry. So you lose about half of your states because you have 4 flavors rather than 2 flavors as as you would have if you only had spin as degeneracy. Also, you lose some of phase space because of backscattering suppression, Klein tunneling, if you wish, and so your effect is, you still get of order 1 exponent, but it's not as strong as it might have been if let's say, I had n equal 4 and no backscattering, and backscattering was allowed, right? So graphene is definitely a candidate, and there are many people, well, not many, but at least a few people I know who are working on placing graphene in polar environment and trying to make it superconducting, we'll probably hear something about it in a couple of years. But meanwhile, as we've been working on it, this paper appeared in the archive, which I think is very related to what I've been discussing. So this is an experiment from Beijing, where they work on, so this is not graphene, but it's a single layer, 1 atom thick films of iron selenide. And iron selenide, bulk iron selenide is a superconductor, but TC is not anything extreme, 10, 20 Kelvin or something like that. But it turns out that if you make it a single layer film and place on a substrate, and they used strontium titanite oxide substrate, you find that it's superconducting up to 100 Kelvin at least, and perhaps even higher because, well, if you look at their data, looks like their superconductivity is dominated by two-dimensional BKT fluctuation effects, and so it's not 100 Kelvin is not perhaps not intrinsic value, but is value after fluctuations suppress the intrinsic value down to slightly lower value. In any case, they have critical current which is non-zero up to 110 Kelvin or so, and so this is potentially an example of what I've been talking about. There is still, debate and discussion and theoretical work going on, but probably the first example of this atomically thin material becoming superconducting because of being surrounded by polar substance. Any questions on that?
Are there experimental examples of this polar mechanism?
Of what?
Of this polar mode. Are there experimental examples of this?
This is only months old,
Right.
and probably the first one.
Okay, yeah.
They've done work before, so this is not their first paper. They're studying the system for about 8 years, and they had STM data that showed gap opening up at temperature below 100 Kelvin, and the gap was BCS-like, density of states was BCS-like, and so they concluded it was superconducting. But because their systems samples are too small, so they're even smaller than graphene flakes. You see, they deposit it, they grow it by MBE on STO substrate, and then they do STM to characterize the system, and then they find that there are small areas about micron size where they can identify complete single layer material, and so they use this technique of 4-point probes, which are made like this. And then they plunge this thing into one of those flakes and do 4-probe measurement. So it's not an easy experiment, but this is the first transport data, and I think that looks very convincing. There's also temperature dependence and B dependence, if anyone is interested. So, yeah. So the question really is what's the limit? We can probably well, if we formulate this theorem and try to prove it, may discover that it can still be an order of magnitude higher than these numbers. Because really, I mean, if you work with Coulomb interaction, then there is no other scale than electron volt. Really, right? So, yeah. Okay, I think, right, so I originally planned to talk about some graphene topics, superconductivity in graphene and correlation effects in graphene bilayer, but I think in 5 minutes left I would rather end early. Okay, so questions?
Since you want to talk about some superconductivity in graphene, do you suppose the mechanism is due to the fluorescence, or and what's the pairing mechanism in graphene?
Yeah. So okay. So graphene is. So let's start with graphite. Okay. Graphite doesn't have intrinsic superconductivity, or maybe it does, but it's too small because electron-phonon coupling somehow is too weak. The reason is probably that graphite is non-polar, right? However, graphite can be made superconducting if you dope it. There is chemically intercalated graphite. If you intercalate it by alkalis, you can get temperatures as high as 10, 12 Kelvin, right? Graphene, I think people will try to intercalate graphene. Maybe we'll have more luck with bilayer graphene or trilayer graphene than with single layer graphene, and see if they can get superconductivity along the same lines. Intrinsic electron-phonon interaction in graphene is perhaps very weak, but one can follow several other routes. One can either try what we discussed, to place graphene in some polar environment, and then there'll be some strong polar phonons in the environment, and electrons in graphene will be coupled to these phonons. Or one can follow a different route, and that's in this paper that we wrote 3 years ago, where you use pure Coulomb interaction effects, no phonons. But for that you need to dope graphene heavily to the point where you reach saddle points in graphene band structure. Maybe I'll just show you one slide. How do I do this? Okay. Right. So if you, so if you take graphene band structure and look at it on a larger scale than we did so far, then there are saddle points over here, which are somewhere between this hill and that hill. So they look like mountain passes around us, right? And if you may see it better in projection, if you draw contour plot, then contour plot will look like this, and there are these saddle points. So saddle points are interesting because density of states there is divergent because of Van Hoff singularity, and so people proposed a long time ago that if you have a saddle point and you dope material to the saddle point, because your density of states goes high, your superconductivity will be enhanced because density of states appears in the exponent, right? That is totally true. However, in systems with saddle points, you often get competition between superconductivity and other types of order, spin density wave and charge density wave. The reason is that in crystal structures with saddle points typically come in pairs or in triplets, and so they are nested, like in square lattice, simplest square lattice Bloch band structure, where there's a diamond-shaped Fermi surface at half filling. Then you have two saddle points, and they are nested. And so if you try to work along these lines, trying to introduce density of states as an enhancement of superconductivity, and then you find that other competing effects, spin density wave, charge density wave, are also enhanced, and so that's the issue here: how superconductivity competes with other orders. And so what we have to stop, but basically one can do analysis for graphene for pure Coulomb interaction, no phonons, internal, external, Coulomb interaction only, and then what you find is that because of this, because of having several valleys, in this case, Coulomb interactions lead to superconductivity, which wins over other orders, and you get no time to write on the blackboard. Let me just show you what this is like. So you get a formula for TC where instead of the interaction strength, there is a square root of it in the exponent. The reason for square root is that if you do the same calculation as we did to derive BCS formula, there will be two log divergences, one from this integral over epsilon that we discussed, and then the others from von Hoff singularity. So your equation will look like not like 1 equal coupling strength times a log, but 1 equals coupling strength times log squared. And so you get a BCS-like formula, but with a square root and exponential. And the square root, if coupling is weak, will make this much larger than without a square root. And so in this way one can access superconductivity, which is pure Coulomb interaction induced, and because of that the prefactor is not over the Debye energy but over the bandwidth, and also the coupling strength is entering under square root, and so it's exponential suppression is not as dramatic as for BCS. Okay, sorry, it took too long to answer that. Any other questions?
This is for long-range Coulomb or for Hubbard-like repulsion?
No, so this was this was for short range. So you start with repulsion, but then you project it on states near the Fermi surface, and then when you do that, your wave number is a order of K Fermi, but K Fermi for this Fermi level, which is somewhere near the saddle points, is a order of graphene lattice constants. So it's essentially it's Hubbard.
But then what makes it qualitatively different from a square lattice? Because square lattice, if you do this, you get
right.
an N order. Somehow that's the spin density wave that wins. And you said it's
that's right.
So you have nesting and
so it's similar. However, so now we have to. Don't force me to give this talk. If you study the competition between different orders, then you find that in the square lattice, the different couplings that appear can drive. They all diverge, and they can drive system in a superconducting state and also to a spin density wave state. And in the square lattice, it's basically it's a messy problem which is still unsolved. And then in this case, because there are 3 saddle points instead of 2, and this is the only difference, the RG equations look very similar, but they pick a unique state. The RG flow picks a unique state.
You're saying that spin, that's the wave, is not even diverging the corresponding.
It's diverging, but the divergence slower. So you have to compare divergence and find the strongest diverging state, which will win at weak coupling, and it will be this state. Anyway, so I think we should go for lunch.